right? Okay, so this is recorded so that if you wanted to double check on a deadline or something like that, that can be, you can go check on there. So as you've noticed, I've started emailing out each week at the beginning of the week what will be due that week and what I hope to get accomplished that week so that we can kind of keep on track and be on page. So this week, I wanted to see if everybody could get to watch chapter 8 and 9 videos on YouTube. And then I've taken some comments from people about it's easier if I could write on the slides while I was talking. And so chapter 9 has all of those with annotations on it. From now on, all of them will incorporate that kind of handwritten notes as we go along. It makes it a little bit longer, but I think it's a little clearer for a lot of people to see that. So chapter 8 and 9 homework are due now Wednesday. I've moved it so homework's due on Wednesday. So in theory, I should have the week's chapters up by Friday of the previous week. You'll have Monday, Tuesday, Wednesday to listen to the videos or watch the videos and start doing the homework. And then you'll have Thursday to kind of review, and then we'll have quizzes on Friday, okay? Due to some technical difficulties with Sapling, I was unable to do that quiz last week, but I think I found a new way to do the quiz. And so what we're gonna do is on Friday, you'll access, in fact, you should get an email, hopefully, from Tracks saying that there has been something added to your Dropbox on our track site. And what you'll do is you'll go and I'll put it up as a Word document so that you can actually go in with Word and edit as needed. And then you can add all the questions. What it's going to be is about 10 questions of what's the product of this reaction and why. So it's only going to be like a 1-sentence answer, or you know that follows this rule, etc. And so it's going to be kind of think about the answer and why you have the answer that you're writing down. And so you'll have all day on Friday to do that. If you have to work on Friday and that timeline is not available to you, go ahead and email me and I'll set up a different timeline for you. But then you'll take that answer, put it back in Dropbox, and my grader will go into each of your boxes and grade as we see, as he gets them in, okay? So that covers all of the things for this week. I've already started recording chapter 10 and 11. Those should be up by tomorrow. It gives me Tuesday and Thursday to do a lot of videos because I don't have office hours. So I'll definitely have chapter 10 up today and up tomorrow. So that'll get us moving right along. So I've updated our schedule a little bit in the fact that if we can get through chapter 8 and 9 this week and chapter 10 and 11 next week, on Friday, what we're going to have is we're going to have the same style of quiz. It'll be a take-home quiz. You'll have the 8 hours to do it. I will upload it to your Dropbox. You can write the answer and why, and then upload it, and then my grader will grade it. And then the following week, the week after next, we'll do chapters 12 and 13. Then we'll do 14, 15. And then on the final week of our semester, we'll do chapter 16 and a review. So I'll go over a lot of things about reviews and about how to, prepare for the exam. When will the take-home quizzes from spring break be graded? A lot of them have been graded, but they aren't all because of a forwarding issue with my grader. We're working on getting all that hopefully done by next Monday. But I have posted the key, so that way we can go ahead and study at least what you have, but it'll be graded, and the grades will be posted by preferably next Monday. okay. Yeah, I guess the exam is scheduled for Wednesday. What I will do is, yes, we're going to keep that. It's going to be released on Tuesday night, and then it's due Wednesday. So I'm sorry, yeah, the second exam will be given out on Tuesday, and then it's due Wednesday. What we're going to do is I'm going to release it in Dropbox, and then you have to put it back into Dropbox for the greater grade. And I'll send out additional instructions on that as our 3 things to do for next week. But we won't have a quiz that week because of the exam, but we will have a quiz on the after chapters 12 and 13 and after chapters 14 and 15, and then we'll just review for the final exam. Excuse me. Okay. So we will have that one exam and then a couple more quizzes. I think we're end up 1 quiz short, and so I will adjust the grading scheme to adjust for that. I'm still going to drop 2 quizzes, so we'll try to get through that just fine. Update on the lab. Okay, so your lab instructors and I have been. We went into work yesterday and actually recorded several of the labs. We're going to finish the last lab today. What I'm going to do is I'm going to start releasing those this week, and I'll send out a separate.
I'm muted. Can anyone hear me?
Yeah, we can hear you, Ben.
Got it. That's a bummer.
So there we go. All right. So update on the lab. I'll start releasing that video of our next lab, which is the Skittles lab. It'll be released on one day, and then you'll have an upload to your Dropbox that is the empty post-lab fill out. Go ahead and review the lab, and then go ahead and fill out the post-lab fill out. There will be no quiz, and the quiz will be, the grading scheme will be adjusted for that. So I want you to watch the video, and then I'll have a couple questions about that with the post-lab quiz. And so you'll get the idea of what was kind of happening. And each of you will have an unknown for the ester lab, which is the follow-on lab. I will upload to your Dropbox what it smells like and have you identify which one you think you had. So that'll be part of your post lab. And then the last one, the qualitative analysis of carbohydrates. I will give you a filled in answer sheet, and you have to identify which carbohydrate you had. So each of you will have a separate one delivered into your, something outside, I think. And each of you will have that delivered into your lab Dropbox as well. So I will send out a separate email for that, but just so you're going to be expecting that. Hopefully, you will just have one of those per week for the next 3 weeks, and then that will finish the lab. You do not have to check out a lab, and we are not going to have a lab final. So by turning in all 3 of those post labs reports, that will satisfy our laboratory for this semester. So I will send out an email on that as soon as I can release the first video to our video playlist on YouTube. Okay, so I believe that covers all of the administration so far, and so we can actually look into doing problems. Does anybody have any questions about what's happening in the class or in the lab for the next 2 to 3 weeks? The next the exam will look a little different because of the idea that we are going to give an open book, open note test. The lab, the exam is going to be more of, name this structure, and so you have to write the name, draw this structure, draw that structure. If we do a reaction, I want to say, what is the major product of this reaction, and then explain why. So it's going to be a little more fill out the blank kind of words. A little more fill in the blank, but I think that gives you an idea of Okay, so I'm going to figure out exactly what's happening with the reaction. I'm going to draw the reaction and explain why. So it's not as going to be as it's not going to be multiple choice like the previous ones where you would be able to discern the answer. You have to actually write it out and complete. You know, and the why is just a one sentence, or it could be, you know, of just a few words. Okay. And for those of you who are chiming in, I am recording this so that you can watch this at a later time if you lost your notes or wanted to get additional information from this information. The exam will be 25 questions. Yes, I'll fill in the blank. It will be on the Dropbox, and you just have to turn it back in. And then for the quizzes, there'll be actually 10 questions. Fill in the blank and why, and then that'll be in your Dropbox as well. The final is actually going to take place in a 2-hour period that we would have had our final on. So it'll be a little, you won't have all day to do it, but you'll have a 2-hour time period to log in and do it and complete it. So the final will be closer to multiple choice, but it will have some open questions. But I'm still working out the details on exactly how to administer that. But I'm trying to find, you know, best case scenarios from everybody around. Okay. Any other administrative questions while we're here together? Okay. So what I'd like to do is, if nobody has any specific questions about Chapter 8 or Chapter 9, I can go in and talk about some of the reactions in Chapter 8 and then talk about some of the reactions in Chapter 9 that I think are important and why they're important. So go ahead and either unmute and ask or put it in chat, and we'll answer those questions first. If not, I'll start sharing my screen with my iPad here so that I can actually do the writing on. And let's see, share screen with my iPad. And this. Okay, so these.
Actually, I do have a question. Can you hear me, Dr. Irvin?
Yes, I can.
Okay, so I was doing the Chapter 8 homework, and I was curious about oxidizing agents with the alcohol group specifically, knowing when it's going to turn into a ketone or an aldehyde. I was able to sort of guess and get those questions correct, but I don't feel like I fully understand when an oxidizing agent will turn an alcohol into a ketone or an aldehyde when doing a substitution or elimination. I was wondering if you could give some examples.
All right. So yes, I will do that. In fact, I'll spin off to that real quick here. And so dehydration, oxidation, oxidation right here. Okay, so there are two things to think about when we're oxidizing alcohols and we want to get to a ketone or an aldehyde. The first thing is we can only get to a ketone if we are oxidizing a secondary alcohol, okay? So if you have a secondary alcohol, meaning that you have, and let's get to my drawing pencil right here. All right, so if we have a secondary alcohol here, okay, those are the way you make ketones, okay? You can use the strong chromic acid derivatives to do this. And the reason it works is it oxidizes off this hydrogen and it takes off the hydrogen here to give you that ketone, okay? So that's how we get to ketones, okay? If you have a primary alcohol, you cannot make a ketone out of it. The reason is that if you have the primary alcohol right here, and you take away a hydrogen here, right here, there's no other carbon bonded to that primary alcohol. Okay, so the first thing to look for when deciding whether it's going to be an aldehyde or a ketone is to look for whether it's a primary alcohol or a secondary alcohol. All of the oxidizing agents we have here will oxidize secondary alcohols to ketones. So think secondary ketone, boom. Ketone, sorry. All right, so now if you have a primary alcohol, there's two things that can happen. If you have a primary alcohol and you use a strong oxidizing agent here, it always goes to the carboxylic acid, okay? So a primary alcohol will always go to a carboxylic acid if we have chromium oxide or this chromic acid oxidation, okay? To stop that oxidation at halfway point, what we have to do is make it a less strong oxidizer. And the way we make it a less strong oxidizer is we turn it into this chlorochromate ion right here. So the only reagent we have that'll stop the over-oxidation is to make this PCC. So now the conditions are primary alcohol and PCC will give us an aldehyde, okay? Right here. If you have a primary alcohol and you don't have PCC, you just have the chromic acid part, it will oxidize, over-oxidize down to the carboxylic acid, okay? So that's how tell the difference between going to the aldehyde, going to the carboxylic acid, and going to the ketone, okay? Now, so we have a primary alcohol that we can make an aldehyde or a carboxylic acid. We have the secondary alcohol we can turn into a ketone, okay? What about tertiary alcohols? Well, because there's no hydrogen on the carbon the OH is on here, it can't take away this hydrogen and another hydrogen because there isn't one there. So they don't react. So they resist that oxidation, and so therefore we don't have any of these tertiary alcohols reacting with us. So primary can be aldehyde with a PCC only. The primary can be a carboxylic acid with the chromic acid. A secondary can be ketone. All right? Does that answer your question then? All right, let's see. Open my chat here. Okay, all right, great. Actually, that's a great question. That was one of the reactions I was going to go over. So, okay, so one of the other things, in fact, well, we're down here already. We only have one reaction really that ethers do, and it's only the three-membered ring. The four-membered ring, five-membered ring, six-membered ring ethers are very, very stable to most things unless you have it really hot and a lot of acid. So the only reaction of ethers we really care about is the one with the epoxide, and that's this three-membered ring here. Three-membered ring. So it's this epoxide, and it does one cool thing is when it's attacked by a nucleophile, it opens up. Okay, that's the major reaction it does. And this is how we make it. We can either make it with oxidizing it, or we can make it by another way. But the cool thing that epoxies do, the epoxides do, is it opens the ring. Okay, so if it's equally substituted, where it has a CH2 on this side and a CH2 on this side, it doesn't matter which side it's going to attack. It's just going to open up. The alcohol is going to be on one carbon, and whatever the nucleophile is, going to be on the other. However, in this case here, we actually have this methyl group here. Whenever it's substituted such that you have a group on one side, right here, that means the nucleophile is always going to come to the other side, okay? Which means your alcohol is always going to be on the side with whatever this group was, okay? So this is the key in that ring opening of epoxies, is that alcohol is always going to be on that side, and your nucleophile, which I will draw here in blue, is going to be on the next carbon over, which is the beta carbon right here. These are labeled wrong. This is the beta carbon, this is the alpha carbon, and this is the, so the nucleophile right here always comes into the other side and opens the ring up, giving us our more substituted alcohol on this side, and our nucleophile attacks the other side. Okay, so that's the key reaction in ethers we have. Okay, so let's go back up. Any more questions on that, on ethers while we're here? So that's the primary reaction we have to care about on that. We make them by, closing up, reacting an alkyl halide with an alcohol. That's how we make an ether, but this is how the only reaction ethers do. Okay. All right, so that being said, I wanted to hit a couple reactions up here in alcohols. The first thing is that alcohols can act as acids, or alcohols can act as bases, okay? Kind of like water, okay? So it's just like water with one carbon group on it. So we have to think, okay, it can act as a base or it can act as an acid. In this case here, it's acting as an acid and can donate that proton here to water to give us our alkoxide, or our salt of our thing, plus the hydronium ion, okay? So this happens a lot where we actually use it as an acid in some of our other reactions. Think about our SN1, SN2 reactions. We actually used it a little bit this way sometimes. The other thing is, because of the lone pair here and here, it can act as a base. So it can abstract a hydrogen from something more acidic to give us our protonated alcohol and our conjugate base system. So that's an important feature there, because sometimes we can use that to our advantage. For example, the first step in a lot of our dehydrations is actually the formation of this particular material here. We actually protonate that alcohol first before it loses that OH. So let's look at some of those other reactions right here. Now this one I had a question with last time, and I think we answered it, but I wanted to say this is a slightly different reaction to what we're used to, because usually we do just an acid or base. In the reaction with an alcohol like this, we are actually doing an electron transfer. We're actually oxidizing the sodium. So the sodium is actually giving away an electron to the system. When it gives an electron to the system, the oxygen already has all the electrons it needs. So what it ends up doing is reducing the hydrogen here from hydrogen plus to having hydrogen neutral. And then the second equivalent of it takes another one, reduces another one to hydrogen neutral. And when it does that, that means these two can form together and form the diatomic hydrogen. So 2 electrons have been transferred from the sodium to a hydrogen, from a sodium to a hydrogen, to give us hydrogen gas plus 2 equivalents of sodium, and it gives us our salt. The actual alcohol only participates in the fact that the hydrogen on it is reduced down. The alkoxide formed is what we can use now as a nucleophile, or use it as a base. Okay, so we're actually transferring electrons here, which is not something we normally do in these reactions. So that's kind of interesting right there. Okay, does that answer anybody have questions on that while we're here? Okay. All right, so then one of the other reactions we have is that we can actually take alcohols and react with a lot of, typically you have to have a very strong acid to create, the alcohol is converted to the halide, okay? And if you think about this, this is a substitution reaction, right? And we typically use these with strong acids because we can protonate that alcohol, making it a better leaving group, and then we can get the halide on here. Okay, so at low temperatures, we can make this reaction happen pretty quickly with any of these strong acids here. But with secondaries and tertiaries, it doesn't really work under these really mild conditions. Okay, so let's see about how this converts a bit. If we have these tertiary alcohols, we can actually do it by having a large amount of this gas available to us. Notice when we do these reactions, we're actually removing water from the system. So the less water in the system, the better. So in the case where we have water insoluble systems, we actually use a high concentration of acid and we bubble it through to create it, or we use a high concentration of acid in water to drive the reaction to completion. We're trying to make more of this by having a whole bunch of the acid available to us. If we have a primary and secondary alcohol, we can actually use this same condition where we can bubble in a gas to create our alkyl halides here. But it requires highly concentrated HBr, or else basically the reaction's trying to go backwards. Remember, we actually converted alkyl halides to alcohols in the presence of bases and water. All right, so how does this work? Okay, so like I said before, that alcohol can act as a base. And so the first thing that happens in this reaction with the tertiary alcohols is it actually protonates the alcohol here, giving us this as an intermediate here, okay? This oxonium ion, okay? So what this means is if this were to leave as a leaving group here, this would have to leave as hydroxide, which is a very poor leaving group, okay? Now, if this were to leave as a leaving group, it would leave as neutral water. So that would be a pretty good leaving group because it's neutral, okay? So that's why hydroxide's a poor leaving group, but water is a better leaving group, okay? So the next thing that happens is we actually break the bond. We have water leave our system here, and we form our carbocation. Now, this happens with our tertiary alcohols because our tertiary carbocations are our most stable carbocations, okay? So it's able to create this stable tertiary carbocation plus a neutral molecule. That's the driving force on this, okay? That's the slow step, but that's still, once we form this carbocation here, now we can interact with whatever nucleophile we have available to us. In this case, if we have chloride ion is a stronger nucleophile than water. And therefore, because chloride ion is a stronger nucleophile than water, it comes in and reacts to give us our tertiary alkyl halide. Okay? So that's what happens with tertiary alcohols in the presence of a strong acid. And it happens because the alcohol first acts as a base, creating the oxonium ion. Then it can have neutral water leave to give us our carbocation. And then the chloride ion, which is the stronger nucleophile than water, can come in and react with the carbocation. Okay? So the reaction's different when we think about it with primary alcohols. When we have primary alcohols, we cannot go through a carbocation. So what happens is we end up doing an SN2 reaction. But the first step is the same. The alcohol still acts as our base and protonates first, and that becomes a good leaving group. Now it has to wait around for the bromide to come along and displace it to give us, this is our slow step, is waiting for that bromide to come and displace it. But it displaces a neutral water and it gives us our alkyl halide. So it does do the reaction, but that's why we need a lot more of this. We need concentrated material. We have a lot of HBr around there so our concentration of nucleophile is high enough so it reacts that way. But again, it never goes through that carbocation intermediate. So that's the interesting thing about it. When we have our secondary alcohols, it can kind of undergo either one because it makes a sort of stable carbocation. So if we think about it right here, if we have primary alcohols, it has to do an SN2 reaction because it can't form the carbocation. If we have a tertiary alcohol, it has to do an SN1 reaction because it forms a stable carbocation. And it's has too many groups around it to do that SN2 reaction. The secondary alcohol can do either. And the cool thing is, most of the time it gives you the same product. The only time you'll get a product mixture is the idea that You have some of it go SN2, which is going to give us inversion of stereochemistry, where this one will give you a mixture of R and S because it racemizes. So that's the only thing we have to worry about there. Okay, so primary always goes to SN2 and has to have a large concentration of acid. Tertiary always goes SN1, always forms that carbocation. Secondary alcohols can do either. Okay, I think that is the last major reaction. Oh, yeah, okay. So we can also do what we call the thionyl chloride reaction, okay? And the reason this works is the fact that we actually are forming a better leaving group, okay? So the idea is that the sulfur compound actually reacts with the alcohol here to make a better leaving group. And therefore it gives us this SO2 as it's literally taking the oxygen off here, transferring it to the sulfur, and then this is leaving as a better group. So this is a kind of a cool reaction. We'll see it again when we talk about carboxylic acids using thionyl chloride to convert an OH to a chloride. So kind of keep that in the back of your head because we will use this reagent again. All right. No new chat questions, and we're doing okay on time. So this is an example of how we dehydrate alcohols. I just want to do this one, and then I want to transfer over to the benzene reactions. So, but the key here is that primary alcohols take high heat and lots of acid. Again, acid's first steps of protonating this to give us our leaving group here. It takes a little less heat to give us our secondary alcohols, but they will eliminate as well. The idea is you're going to protonate this first, and then that makes it a good leaving group, and then that eliminates and regenerates your acid. Now, your tertiaries obviously go at the lowest temperature because they can form that carbocation first, then eliminate the hydrogen. So that means that they can move along a lot faster, okay? Any questions on alcohols before I move to benzenes? I want to have a couple of reactions on benzenes, and then that should take us to the end of our time today. All right, chat now or forever hold your peace. All right, I'm going to move over to benzenes then. Okay, now in the benzene system, I'm assuming you're going to go ahead and look at the nomenclature, so I wanted to look at the reactions themselves. Okay, so the first thing I wanted to remind you is that to be aromatic, you have to be a ring, have a p orbital on each of the atoms in the ring, be planar, and have a certain number of electrons. Most of the time, we're going to be dealing with 6 electrons, 1 or 2 electrons in each of those p orbitals. It's funny because to get the right number here, remember when we had those 5-membered rings, we actually had 2 electrons in the p orbital to give us our total of 6 electrons. And we can actually have 0 electrons in a p orbital to make sure we have the right number of electrons too. But most of the time, we're going to have 1 or 2 electrons in that p orbital, and we're going to have 6 electrons in that system, okay? That being said, I want to move over to the first reaction is the benzylic oxidation. Notice this uses the same reagent we used when we oxidized down the alcohol. Here it's the chromic acid system. The key is you have to have a hydrogen here. There has to be a hydrogen here to get this oxidation to work. If you had a T-butyl group or something like that right there, this would not work. You have to have a hydrogen there. So that's the important part, is that hydrogen on the benzylic oxidation, okay? And most of the time you oxidize it down to the carboxylic acid. If you have a longer chain, sometimes you can stop at the ketone. All right, so this is used a lot. You can use it for anything with this benzylic hydrogen on it. It will convert to a carboxylic acid. Oops, all right. The next most important thing is what we call these substitution reactions. Now, the mechanism of all these substitution reactions is approximately the same. It's all aromatic substitution electrophilic, meaning that something, the thing that's going to bond to your, that's going to make this bond, this thing has to be somehow positive. That's why we typically use a catalyst with this. So the first step in each of these reactions is forming something that's going to attack, and it's going to have a positive charge on it. That's the thing I want you to see, that's continuous through all of these reactions, okay? So in the case of halides, we use this ferric chloride or ferric bromide to do that reaction. In the case of nitrates, we use acids to generate that. We can also use acids to generate a sulfur cation. And the cation is the thing that's always the reactive species in there. So let me show you a couple of these mechanisms and show you that that's why it's always the first step and why it's the important step here. So it works for the sulfonations, the alkylations, the acylations. All of them do that same thing first. They form a cation. That cation is the species that actually does the attack. And then hydrogen is eliminated as a cation, okay? So we have a cation formed, it adds to the benzene ring, and then kicks out a hydrogen cation, okay? So I'm gonna show you one of those mechanisms here. And the first step is always to generate this positive electrophile. That electrophile then interacts with one of the double bonds, giving you this intermediate. And how many different resonance stabilized intermediates you can make tells you how good the reaction is. If you can make 4 of these resonance intermediates, it's going to happen faster and more often than if you can only make 2 or 3 of these, okay? So, and then of course, something comes along. Usually there's a negative charge of something or a Lewis base that comes in and takes away the proton, okay? So let's look at how we form that cation in halogenation. When we form that cation in halogenation, the chlorine bond is nonpolar, right? Because it's chlorine-chlorine, so that's a nonpolar bond. So we actually use that catalyst to pull on that bond to make it polar, okay? So by pulling on that bond and kicking in these electrons, we end up with this chlorine cation. We have to form that chlorine cation first. Once we form that cation, it can now start interacting with the benzene. Notice we now have this negative species here. So this ferric tetrachloride, the ferric tetrachloride here is an anion and will act as a base at the end of our reaction, okay? So the next step, of course, is the attack by the cation to the system, and then resonance stabilized metal. And then the leaving group here is that anion, that new base we just formed, is going to react with the system to kick out our original catalyst and HCl. Okay, let me go through another one and show you it's the exact same mechanism for nitration or sulfation or the Friedel-Crafts reaction. So in nitration, again, we do the same thing. We form this protonated species here that generates, when it decomposes, this electrophile. We have a positive charge on nitrogen here. If you draw the Lewis structure for this nitrogen, the positive charge is actually on the nitrogen, okay? Then that attacks the system and then kicks out our hydrogen again. So we start with an acid that's being protonated by another acid to give us our cation right here, okay? Let's look at that as with the Friedel-Crafts system. In the Friedel-Crafts system, we use this catalyst here, usually aluminum chloride, that's going to generate a carbocation at this center here because we'll form the aluminum tetrachloride anion plus this carbocation. Our carbocation is the one that's going to attack. Okay, so good. We're using the same mechanism for all of these reactions. Let's do it with an acyl group, okay? So again, we're using this aluminum compound to form our species here, which gives us our carbocation. We do the same thing with acylation. In acylation, we end up using the same catalyst, aluminum chloride, it's pulling the chloride away again to give us our intermediate. This is our new base right here, and it gives us an acyl cation. So we have a cation on that carbonyl. So it ends up being, again, the exact same mechanism. First step is always forming a cation. It doesn't have to be a carbocation. It always forms a cation and then does the interaction, and then always kicks out a hydrogen, okay? So we can do this with double bonds as well. All we have to do to generate that cation is to protonate this side right here. These electrons will come up to make that bond, giving us our carbocation here. So it's the same step, except we're using a different acid catalyst to generate our cation, okay? So go through every single one of those reactions and look at it. It always does this, and then it always kicks out a hydrogen positive, the hydrogen cation, as in the last step. So I think that's really nice to kind of figure out and see that it's all the same mechanism. You just have to make sure you know which catalysts work with which, okay? When you're doing an alkylation or acylation, you use aluminum chloride. When you're using an acid, you can make the nitrogen cation, the sulfur cation, or a carbocation. In the case of like this alcohol here, it protonates this and forms the cation. But when you're doing halogens, you have to use ferric chloride or ferric bromide. Okay, so you have slightly different catalysts, but you do the same mechanism each time. Okay, so then when this slide right here, which is on the slides there, I think sums up why once you have one group on there, it activates or deactivates a system. And I went through showing you the different resonance structures here. But another thing we can think about, and I said it on the slides, but I want to draw your attention to it again, is when we have these lone pairs by themselves, those are always strong activators. When we have lone pairs next to an electron withdrawing group, like a carbonyl, they're still activators, but they're not as strong because that carbonyl is pulling some of those electron pairs away, okay? Right here, when you have carbon-carbon bonds, they're not really activators because that's a nonpolar bond, but they don't inhibit anything either. So we call those weakly activating, okay? Now, because all of these actually pull electron density away, they slightly deactivate. But because they have lone pairs, they direct orthopara, okay? Now, when we go to the meta-directors, all of these have carbonyls or some kind of partially positive charge on them, or they have, if we look at our resonance structure, there's a positive charge on nitrogen. There's a formal positive charge on nitrogen, formal positive charge on nitrogen, or this has so many electron withdrawing groups on it, it's pulling all the electron density away. So these two groups are what we call strong deactivators, as well as anything with a positive charge on it. So when looking at the second substitution, does it have a lone pair on it? Ooh, it's probably an orthopara director. If there's a carbonyl on it, it's not as strong an activator as if we didn't have that. Carbons are not donators or not really activators or deactivators. Halogens are inductive activators, but in net, they are deactivators because they pull electron density away. And of course, our deactivators are partially positive or fully positive charges. Okay? Questions on that? I think this kind of, if you can get this kind of trend in your head, it makes it easy to take any functional group and say, oh, lone pair on here. Ooh, lone pair but a carbonyl. So you'll kind of have an idea of where to go. And then if you think about, oh, it has a carbonyl or a positive charge right next to the ring, it's probably going to be meta and it's probably going to be deactivated. Okay, so if you can get that trend in your head, you can do almost any functional group just by kind of talking yourself through it. Okay, that gets us pretty close. Let me see, I think I have one more slide on this. And so, yeah, and so this slide is kind of the helping you kind of think through the system, exactly that system that I was telling you about before. And the idea here is that if you want the group to be in a certain place, you have to direct it to that place. So if we want our group here to be opposite our group, we have to think, okay, our first group here, if we had that group on there already, that would actually be a meta director. So I have to have something else there first. So we actually just reverse the order of the reagents right here to change that, okay? So if we nitrate first, because this is an orthopara director, we can get our nitro group here, and then we oxidize, do that benzylic oxidation, because we have hydrogens there, to our carboxylic acid. We will get to this para substitution, okay? If we already had the carboxylic acid there, we would get meta substitution, okay? So if we want meta substitution, oops, what we do is we go ahead and oxidize it first, and that's going to direct meta, and that means when we do the nitration, we're going to get it in this position here, okay? So the idea here is that by knowing what our two groups are here and here, we know we can do that. We can say, oh, these are both meta directors, so I have to do it in this order. This is a para director, this is a meta director, so I have to do it in the opposite order. So that's just kind of thinking through the orthopara direction and the activation deactivation system, okay? All right, so that's all the slides I wanted to talk through and kind of give you some, let's see, I'm gonna stop sharing. That's what I was going to talk through and kind of draw your attention to look at for the next homework set and for our quiz. Does anybody have any additional questions that I did not cover? Let you type away here, or you can just unmute and ask me if you want. Okay, we do have a few minutes. If you have a question, go ahead and hang on. If you don't have a question, go ahead and log out. I will stop recording and I will post this to the YouTube channel if you wanted to do anything like review any of our notes, okay? So I'm gonna stop recording.